ago we talked about the idea of electric flux. If we have a loop and you are shining light through the loop, then the maximum amount of light gets through the loop when the loop is oriented this way relative to the light coming this way. If I turn the loop like this, you get less light through. You turn the loop like this, you get no light through, right? And so as this thing rotates, you can get more and less and more and less light. Replace the light with an electric field and you get electric flux. Well, replace the electric field with a magnetic field. Just stick a magnet here and start to rotate it, and the amount of magnetic flux that you have going through a loop will change. So the amount of flux that you get is equal to the magnetic field strength times the area times the cosine of the angle between the plane of the loop and the magnetic field. Flux equals BA cosine theta. Well, Michael Faraday discovered that you can create a voltage simply by changing the magnetic flux through a loop. You can do that in a lot of ways. If the loop is squishy, you can make it bigger or smaller. You can move the magnet closer or farther. You can rotate the loop. And any way you do that, anytime you change the flux, you get a voltage. And the relationship is extremely simple. The voltage you get is equal to the rate of change of flux. That's it. The faster you change the flux, the more voltage you get. And that is a very, very powerful law. The equation looks like this, and that n is the number of loops. If it works for one loop, then 2 loops gives you twice as much voltage, and 5 loops gives you 5 times as much voltage, and so forth. And so the more changing flux you have, the more voltage you get. And it sounds like you're getting something for nothing, doesn't it? Well, it turns out that it's harder to change the flux through 5 loops than it is 1 loop. So there's still conservation of energy, your power in, power out, stuff like that, all still has to balance out. You're not getting something for nothing. This little negative sign on Faraday's law is called Lenz's law, and what it says, in essence, is that however flux is changing, the current that gets induced by that changing flux is going to fight the change in flux. It's like nature always wants the flux to be the same, and so if you try and change the flux, nature induces a voltage to try and fight that change in flux. The details as to why that's true is way beyond the bounds of this class, but we discovered that it is true. And so let's do an example or two. If I have a ring of wire, and I have a magnet here with a north pole, this is the north pole here, and I take this magnet and I pull it downward, the upward flux is decreasing. So which direction is current going to flow in the loop, this way or this way? Well, how do you fight a decreasing upward flux? Well, you create an upward flux, and the right-hand rule tells us that that means current would flow this way through the loop. If I take my magnet with my north pole and I bring it up near, then in bringing it up near, the upward flux is getting stronger. How do you fight an upward flux getting stronger? With a downward flux, and that means current is flowing this way. Those reverse if you have a south pole. If I've got a south pole here and I pull it downward, that means I have a downward flux that is getting weaker, so I want to make more downward flux, and it's going to flow this way. Lenz's law with a right-hand rule is an important thing that you're going to need to know how to do for the AP2 exam. This idea that changing magnetic flux can create a voltage is enormously powerful, and we have a ton of technology that we have created using it. For example, we have ground fault circuit interrupts. This is a tiny circuit breaker that detects a change in flux so that when electricity flows out through an appliance and back in, that's what you want to happen. If you're in a wet environment like a kitchen or a bathroom or a greenhouse and it flows out and then doesn't come back in, that means that some of the electricity went into the ground somehow. So let's take a look at a ground fault circuit interrupt and how it works in a little more detail.
So this lead resistor here is your hair dryer or whatever you happen to be using in a wet environment. And normally electricity is flowing in and out through the wall right here. And we surround that with a transformer, basically with a big piece of iron, and we wrap that iron in some loops of wire. That means that when electricity is going in and coming out at the same time, you're not getting any changing flux through those loops. And that's good. You're not going to have a problem. But if electricity suddenly starts flowing out of the appliance into the ground through, unfortunately, your heart or something, then you're going to have a real problem, and we want to turn it off really fast. So you get a flux that suddenly changes in this little sensitive detector. That leads to a sensor relay which pops the breaker. And so this thing works because of electromagnetic induction. Normally, the total flux through the loop doesn't change, even though this is alternating current and it's going back and forth and back and forth. However much is going in is exactly equal to however much is coming out. Well, you interrupt it, and it interrupts the circuit. That's the whole idea.
How about this one? An electric guitar works through electromagnetic induction. You have what's called a pickup, and that pickup is a magnet with little loops of wire around it. Electric guitars use metal strings. The magnet causes the string to magnetize like our paper clips did before. When that magnetic string vibrates back and forth across the loop, it causes a voltage that changes at that same frequency. You can feed that voltage into an amplifier and then into a speaker and create yourself a sound with the same frequency as the electric guitar. A very, very similar idea for sleep apnea monitors. Sleep apnea is when you simply stop breathing while you're sleeping. It's not very good for you, and most people will sleep very fitfully. They won't get a good night's sleep because their body is constantly waking up. A sleep apnea monitor can be a very important thing, especially for very young children. There used to be something called SIDS, Sudden Infant Death Syndrome, that we have almost eliminated through sleep apnea monitors because a kid would just go to sleep and then stop breathing and then never start again, and that's very tragic. What you can do is put a monitor on the kid's chest, and as the kid's chest is rising and falling, if you've got a magnet and a loop and they're moving with respect to each other, then you're getting a constant signal that's going to a little alarm that says, don't go off, don't go off, don't go off. And if that breathing stops, then the alarm goes off. And when the alarm goes off, it wakes the baby up. As soon as the baby wakes up, they start to breathe again, and they're okay. That's a huge, huge medical advancement that has helped avert a whole lot of tragedy in recent decades. We have door alarms and anti-theft devices that are functionally identical to a guitar pickup. If you put a magnet in the door and a loop of wire and a sensor next to it, when the door opens, it changes the flux through the wire, which can be hooked up to an alarm or a beep or whatever else. You tape a little magnet to the bottom of a vase in a museum, and beneath that you've got a loop of wire. Someone moves the vase, you detect it. Cool, right? This is how trip lights work. When you drive and there's a light that's always red one way, but when you pull up, it'll turn green for one cycle. How does it know you're there? People guess that it's pressure pads or, I don't know, a gnome in the bushes with binoculars with a switch, all kinds of things. People generally don't even think about it. It just works. Well, it turns out the way it works is that you've got a loop of wire under the road. The metal in your car is aligned somewhat with the magnetic field of the earth. So when you drive over it, you change the flux through it and it detects it. All of this technology is based on the same principle. One more for you. We have these things called credit cards. I don't really feel like showing you the front of my credit card, but on the back, you have a magnetic strip, right? The magnetic strip on a credit card is magnetized up and down and up and down, and you take it and you swipe it through a loop of wire. That loop of wire detects voltage one way, then the other, one way, then the other. You get zeros and ones and zeros and ones. You embed a code. This is the way old school tape recorders worked. The back of a credit card is basically an old school tape recorder, except instead of being a big reel, it's one little strip. And finally, one more that is a little bit different that uses electromagnetic induction is critical for modern electrical infrastructure, and that is the transformer. Now, you've seen transformers before on telephone poles and things like that. We call them telephone poles. They're usually power distribution poles. So this is a transformer, and they look like a big can, right? Another place you find transformers is any kind of computer power supply or your phone charger, things like that. They have transformers in them too. And what is a transformer and what does it do? A transformer transforms one voltage to another. Here's what one looks like via diagram. You have what's called your primary coil, and this is your input coil. And then you have an output coil, which is a different number of loops. And here's how it works. current flows into the loops, and that creates a magnetic field. It's an electromagnet, right? The magnetic field usually does this, but because of the iron there, most of it gets carried through over into the secondary coil. A changing magnetic flux through the secondary coil induces a voltage, and because the number of loops are different, it's going to produce a different voltage. Now, it sounds like you're getting something for free here. Hold on, another detail. If you did that and you hooked it up to a battery, you'd get a spike of current on the other side, and then it would stop. Because it's not that you have flux that's creating voltage, it's that you have changing flux. But if you have an alternating current going in, so the voltage is like a sine wave, it's going up and down and up and down and up and down, then this electromagnet in the primary coil is this way, and then it gets weaker and gets stronger that way, and then weaker and then stronger this way, and back and forth, about 60 times a second. Well, that causes a continuously changing flux in the other side, which causes it to continuously generate voltage. It's a very simple relationship. The ratio of turns is equal to the ratio of the voltage. If you have twice as many secondary turns as primary turns, you'll get twice as much voltage out in what we call a step-up transformer. If you have half as many in the secondary than the primary, then you'll get half as much voltage out in what we call a step-down transformer. Again, this sounds like we're getting something for free. Why not just take a step-up transformer, take half the voltage, feed it back into the first half, and then use the other voltage for other stuff, and then do it over and over and over again? Well, because that's not how things work. Energy still has to be conserved. Power is voltage times current, right? Effort times flow. And if you are getting more voltage, you're getting less current. This is not a circuit in the way where you've got a battery and a resistor where it's going to follow Ohm's law, right? This is an electromagnetic interaction. What a transformer does when it steps up voltage is it takes the voltage from many electrons and concentrates that voltage, that energy per charge, into fewer electrons. So you get fewer electrons, each of which have more energy. Transformers are very efficient, 99% or so, and so you get this energy conversion of the power in has to equal the power out. VI in equals VI out. So if you get 10 times as much voltage out, you get 1/10 the current. So you get 1/10 of the electrons flowing, but each one has 10 times the energy. The flip side happens on a step-down transformer. If you have a 10-to-1 ratio of your turns, then you're going to get 10 times as much current out, but you're going to get 1/10 the voltage. So the electrons are going to come out 10 times as many of them, each with 1/10 the energy. So it's always a trade-off. Whatever you gain in voltage, you lose in current, and vice versa with a transformer. And by the way, you don't actually have to have loops in order to get an induced voltage with a magnetic field. Remember that magnetic fields put forces on charged particles. So if I just have a metal rod here, it's got electrons that are free to move in it. The magnetic field of the Earth is about that way. So if I just take this and do this with it, I can induce a voltage in it. Imagine a positive charge inside here. The charge is going that way, and the magnetic field is that way. And so a positive charge would get forced downward in this loop. What really happens is that electrons get forced upward. So when I do this, electrons get forced to the top. Well, if I do this, well, that is now that. Positive charges would go up, electrons get forced to the bottom. So just by doing this, I'm creating an alternating voltage, and current is actually going up and down and up and down and up and down on this. If I got in a car and I drove with this thing, west is the direction I'm facing at the moment. If I drove west, then I would end up with electrons building up in the top, and they would get pushed up there until the charge of the electrons prevent more flowing. So the voltage up at the top is going to cancel the effect of the magnetic field until electrons no longer flow and you have a static situation. In that case, the voltage that you get is BLV, the magnetic field times the length times the velocity. And so that, if you're traveling at an angle, it's going to be BLV sine theta. That's called motional EMF. It's the voltage you get via moving. This can be a problem for things that are moving very fast. Maybe not a car whip antenna, that seems probably not a big deal, but airplanes flying up high through the Earth's magnetic field they're very long, right? And if the motional EMF is BLV, you get this really big wingspan and a very high velocity flying crosswise to a magnetic field. You can end up with pretty high voltages, and so airplanes will often have a voltage generator, a battery of some kind, to actually get that voltage more balanced out so you don't end up with charge buildup on your wings, which can cause all sorts of other problems. This motional EMF is also responsible for a generator. Do you know what a generator is? A generator is just a motor that's hooked up backward. If you force a generator to turn using mechanical energy somehow, a wind turbine, a water wheel, whatever you want to use, steam power is what we usually use. Even in a nuclear power plant, it's steam powered. You get that to turn inside a magnetic field, you generate voltage. This is the other half of the electrical side of the Industrial Revolution. And that generator is really just a motor backwards. They just convert electrical to mechanical energy in the case of a motor, or mechanical to electrical in the case of a generator. This is also useful in, say, the brakes of an electric car. So if you drive an electric car or a hybrid or something like that, when you are driving, if you short the leads to the motor, then the mechanical energy starts to get converted into electrical energy, and that actually does work on the motor and pulls the energy out and turns it into electrical energy that we can feed back into the battery, and we can recover energy that way. This is called electromagnetic braking, and it's very useful. You can't come to a complete stop that way, because you brake harder the faster you're spinning and the slower you go, the less the flux is changing, so the less voltage you're going to generate. But you can at least use that in conjunction with regular brakes to not only brake better, but also recover some of the energy you used while driving. That exact same phenomenon comes up with something I talked about quite some time ago, which is if you have a power outage that is not complete, instead of a full blackout, if you have a brownout. So when you have anything with a motor like a refrigerator or an air conditioner that's running, when you give it a certain amount of voltage, the motor runs and spins, but the spinning of the motor creates a voltage back the other way. We call it back EMF. So if something is designed to run at 120 volts, it's not really drawing 120 volts. If you did Ohm's law through the circuit, it's not 120 volts. It's 120 minus what the motor's doing. And the faster the motor's spinning, the more back EMF it's going to create. So it might be 120 minus 110. Or if you make that motor run half as fast, maybe that 120 drops to 80 volts. Well, 80 volts isn't enough to make the motor run 2/3 as fast. Maybe it'll only run 1/3 as fast. So now it's 80 in, but the out, instead of being 70, the out is only, say, 30. Now you've got 50 volts across your motor instead of 10. It's going to draw 5 times as much current. This can cause fires and short circuits and all sorts of things like that. It's a real problem. When you have a motor that is designed to run at a particular speed at a particular voltage and you force it to slow down, it draws a lot more current. And that's something that you have to keep in mind with everything from electric cars to first robotics when you're driving with a robot that way, or you have a lifting arm with a motor on it. Anytime that motor is not running fast, it draws a lot more current because it's not producing that back EMF. One more thing we can use back EMF for is something we're not going to do too much of here in this class, but you can create what's called an inductor in a circuit, which all it really is a tightly packed loop of wire. So when you have your battery and then you have a resistor, a lamp or whatever else, and then you just have this really tight loop of wire, when you close the switch and you turn that thing on, when current starts to flow through the wire, it creates a changing flux through the loop. The loop becomes a little electromagnet. That flux opposes the current and creates a back EMF. And it creates a bigger one the greater the change in current. And what that does is it fights the current that's turning the circuit on and causes it to turn on more gradually. So if you have an inductor in a circuit, when you close the switch, your light might just come on gradually rather than coming on all at once. Same idea when you turn it off. Instead of just dying instantly, as it starts to die, the inductor detects that, creates a back EMF the other way, and keeps current flowing in the circuit for longer as it dies out. We're not going to do much with inductors. We use them, they often have hundreds of loops in them, and you put them in circuits. How many loops and how big and exactly how you arrange it is outside the bounds of what we're going to do here. But the general idea of an inductor that it can help smooth out current flow. If you have something jittery, if you have a power supply where it's supposed to be creating a voltage like this, or it's supposed to be creating a current like this, and it's instead doing this, by putting an inductor in, when you get these really big, fast spikes, the inductor will fight those and smooth them out. So instead of getting something like this, you'll instead get something like this, which is much more tolerable for what you're trying to do. Inductors are very useful. They're just not something we're going to do too much with now. On a final note, the fact that a jiggle in an electric field creates a magnetic field, and that a jiggle in a magnetic field creates an electric field, is pretty cool. But it turns out that in the 1800s, James Clerk Maxwell figured out that this could only happen at one particular speed. And he calculated that speed to be 2.9989 times 10 to the 8 meters per second. He calculated it to be exactly the speed of light. And it turns out that that is exactly what light is. If you take an electron and you shake it up and down, when you do that, you create a jiggle in the electric field. That jiggle in the electric field creates a jiggle in the magnetic field perpendicular to it. But that jiggle in the magnetic field creates a jiggle in the electric field perpendicular to it. And that traveling jiggle zooming off into space is light. More on electromagnetic radiation, what we like to call light when we can see it, in the next unit.